today I'm going to talk about strongly consistent global indexes for non-transactional tables. This is a new design proposed by Kadir Özdemir. He's an architect at Salesforce. He couldn't be here today, so I am presenting his design. My name is Gökçen İskender. I'm a software engineer, again working for Salesforce. Let's have a quick outline of what I'm going to talk about today. I will talk to you about how the current design for global indexes work, both immutable and mutable. And I'm going to explain what is the new design for, why do we need it, and how is it different for mutable and immutable global indexes. And then we will move on to discuss why the new design approach is correct, the correctness approach. And then we will look at the performance implications. Some terminology. When I say global index, it means that the index data is stored in a separate HBase table physically from the data table. So we create an index on top of data table in Phoenix, and then the global indexes are stored in a different table. And just this for completeness, local indexes, as the name suggests, live at the same place as the data table, on the same table. But this topic does not cover local indexes at all. We will just talk about global indexes. Immutable indexes means once the row is there, it is not changed. We don't expect changes, updates on the row. Mutable means changes is okay. Data can be freely changed. And when I say mutation, it means upserts and deletes. Let's look at how does global mutable indexes work today. So an application does a SQL-like query of upsert and delete to Phoenix client, and then Phoenix client translate them to HBase client mutation batches. And then HBase client sends the request to first a region server for the data table, and there is an indexer coprocessor in the region, which goes ahead, gets the current status of the data row, updates the data row with the change, and then subsequently sends index table changes to index table region servers. For the immutable indexes, again, upsert and delete request comes to Phoenix client, and Phoenix client in parallel sends the mutations to HBase client, and everything happens in parallel. Like data table is updated with indexes in parallel today. So as you might expect, it is very easy that the Phoenix index global index can get out of sync with the data table easily. If you look at the mutable approach, you can see that first the data table is updated, but then while updating the index table, something might happen like RPC timeout, network issue, or server might fail altogether, and the index get out of sync with the data table. And for the immutable one, since they are happening in parallel, in arbitrary order, even the data table update might fail, but you have an updated index, so it is out of sync. So what is the objective of this design change? Obviously, we don't want this getting out of sync issue to happen. So global indexes should always be in sync with their data tables. First objective. Second objective, consistency should not impact the performance significantly. And the redesign, this redesign should not require rewriting of the existing Phoenix code extensively. It should be contained to certain parts of the code, and we don't have to change a lot of things. And we want to eliminate today's index rebuilds, the operational work, simply. So the JIRAs are listed here for this effort. So if you look at Phoenix 5156 is the major JIRA. This design is in code review right now. You can go today and review this code for the change. And before coming up with this design, here are some observations. An index table row can always be reconstructed from data table row. And the second observation is in HBase, writes are fast. So with this new design, we can add an extra write step and hope that we are not severely impacting performance. We also considered two-phase commit protocols like transaction protocols for global index and data table sync problem. But we found that existing solutions are in beta, and we thought that they are too generic for this problem, and it might be expensive. So what is new with this new design? So we will have a new column called verified column. It is not actually a new column per se. It's an existing column called empty column, which is already there today. What Phoenix does is it checks for the existence of this column, but it doesn't check the value of this column. So today, for example, the value of this column is X, which is not checked anywhere. But we want to reuse the value of the column to store the verify information. Again, this is the current empty column. And the new design, we reordered some operations, and we added an extra write phase. I'm going to explain each of them in detail in the upcoming slides. First, let's look at an overview of the current design versus new design side by side to see the difference. So this one is for mutable global indexes. As you know, as I described in the right path, in the current design, we update the data table, then the index tables are updated, and we wish for the best. But with the new design, it is three-phase updates. So we update the index table rows first with verified column equal to false, then update the data table, and as in the third phase, we update the index table again, this time set the verified status to true. In the current design, in the read path, when you query through an index, we read the index rows as they are and assume that they are all good. Even if they might be out of sync, we just read from index rows. But in the read path in the new design, we read the index row and check the verified status. If it is verified equal to true, we return from the index. If the verified is equal to false, we reconstruct the row from the data table itself and then return that in the scan. For immutable global indexes, the new design actually basically stays same. There is new ordering rather than writes going in parallel. The same ordering applies like index table, data table, index table. And in the read path, it is the same again. So this is the detailed explanation of the flow with the new design. It is similar to, as you can see, the graph, the picture is similar, but there are some nuances. So upsert deletes, batch of mutations comes to HBase client. So far it's the same. Then it goes to data table region. There is this indexer coprocessor, which in the first step logs the data rows. In the second step, it gets the timestamp. I'm going to explain why do we get the current timestamp. And then as the third phase, we read the latest and greatest data row, and we compute bunch of mutations to send to index table. And as the fourth step, we release the logs on the data table. And fifth step, it goes to index table regions and updates the index rows with verified flag false. And at this point, if this step fails, we don't continue, we return an error to the client. Sixth step, let's say it didn't fail, indexes are updated. Again, we take the logs on the data rows, we update the update the data table, and in this step, we also detect the concurrent mutations. That's why we use the timestamp that we took at step 2 to detect the concurrent updates happening on the data table. Then we release the log at step 8, and if we detected concurrent update for the row for data table, we don't continue with step 9 of updating index verified status to true, we just return. But if there are no concurrent updates, we go and set the index verified value to true. So in this step 3 of calculating the batches, I'm going to now show you some examples of what I mean when I say calculating the batches. Here's an example of an update. Let's assume we have a data table with primary key or row key value of 1, and it has a column 1 value A, column 2 value X, column 3 value Y, and it has an index on it on column 1, and the primary key for this index row looks like this. It is the column 1 value, which is A, comma, the primary key of the data table, which is 1, and since the column 3 is included, its value is stored there as well. And in our example, we update the value of column 1 from A to B. That's the update. Like on the data table, we update the A. So in the first phase, like I was talking about the verified value false phase, we have two batches here. First, we put the A, 1 row verified value to false, and we insert another row with B, 1, which is the new value, and again, its verified status is false. We update the data table in the second step, and in the third step, we delete the A, 1 value, and we update the B, 1 verified value to true. So why does the delete happen on step 3? Because if we did it in phase 1 and removed it from the index, if the data table update failed somehow, then we would have an out of sync index. That's why deletes are pushed to step 3. And this is again an example of a delete batch, like the same table, same index. Now we are deleting the row with primary key value 1. And first step, we update A, 1 verified to false. We delete the data table row in the second step, and we delete the index table row on the third step. So for the immutable indexes, it looks very much like the the original design, as you see, very similar. The only difference is now Phoenix client orders the operation. They were in parallel before, but now we have the same three-phase update here, like update index table verified false, update data table if it succeeds, and then go and update verified value to true. How about the read path? How do we scan from an index or read from an index? Let's say I have a select statement coming to an index, and Phoenix client translates into a scan, and it goes to the index table region, because for indexes we always read from indexes. Scan region observer in the region server interferes, and we have a new, this is a new coprocessor added, global index checker. Global index checker looks at the verified flag. If it sees the value as true, it just returns it. If the value is false, then we call it read repair, because it goes to data table now, and it just builds the row from the data table, updates the verified flag as true, and includes that in the scan result. So the steps 3 to 5, 6, they are all like index rebuild steps, like today, but we have just the global index checker in between interfering. So why do we think this is correct? Why do we think the new design, once you read the index row, it is correct, or scan the index, it is correct? A disclaimer here, the correctness slides applies to the new indexes created after we have this 51, 56 checked in, or after you rebuild the existing one. So we assume that there is no all the new data residing in the index table for the correctness. So once you read from an index table with verified equal to true, you can assume the row is correct, because this happened after the data table. Because of the ordering, we know that this happened after the data table update. If the verified equals to false, and this is for the without the concurrent updates, we don't even read from the index table if verified equal to false. We always go and reconstruct it from the data table. And how about I can't find any row in index table? Is it possible? Well, it is not possible because we first update the index table in the first phase. And if the index update fails, we still have the row in the index table with verified value equal to false. And next time it is read from the data table, we are going to see that there is no row in the data table, and we are going to remove it from index table anyways. And for the deletes, index row is deleted after the data row is deleted, so we shouldn't have missing rows in the index. What if there are concurrent updates going on? How do we trust the index table value? As I explained it in the previous slides, we detect the concurrent updates, and we don't proceed with phase 3 of setting index row verified status to true. So it will always be read repaired from the data table. With this new design, what is the upgrade effect? We don't have any schema change on the index tables. It is just the existing empty column repurposed as the verified column. So we don't need to do any schema change in the upgrades. But we advise it to rebuild indexes once 51, 56 gets checked in and released, so that you always have a consistent result for both old and new data. How about the performance effect or performance impact? We did a preliminary testing, and Kadir did some, and we have a performance team. They use 1 million rows, I'm assuming. That's what I heard. And you can see the test environment details here where we did the test. We observed, since we have an extra write phase here, we observed 25% in write latency. But we didn't observe any noticeable increase in read latency. Here are some resources. You can also look at the design documents, and if you have any questions, you can put it in the design document. I also added Kadir's email and as the last row here. If I cannot answer your questions, you can always send them an email. Thank you. If you have any questions, I can answer. It is still in code review, so I don't know really. And the first phase of code review is for the mutable indexes. I plan to implement the immutable part once that gets checked in.
What about the secondary index?
This is for secondary indexes. Yeah.
You don't call it a secondary.
Yeah, we call it global and local. Yeah. Any other? I think I finished already. So you guys can.